بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 12 في ال Random Variables and Stochastic Processes. Lecture number 12 تتكلم عن ال Statistical Independence of Random Variables. إذا بنتذكر نتكلم عن ال independence of events. If you have two events A and B, then the statistical independence means that the probability of their the joint probability is equal to the product of the probability of the events themselves. So probability of the joint event is equal to the probability of A times the probability of B. So if we assume that this is the event A is x less than or equal small x and y less or equal small y, then this is equals probability of x less than or equal small x times probability of y less or equal small y, which means that the distribution of the joint of x and y is equal to the marginals fx of x times fy of y. Of course, if we do the partial derivative, so fx y of x and y, which is equal to the partial second fxy of x and y partial x partial y, this is also equals to the fx of x times fy of y. So we can check the independence in terms of the distribution or in terms of the density. So if the marginal densities, the product of the marginal densities equals to the joint density, or the product of the marginal distributions equals to the joint distribution, then you have statistical independence. Okay, let's see this through an example. We have an example here. Fxy of x and y equals to 1 over 12 u of x, u of y, e to the minus x over 4 minus y over 3, and we would like to determine if x and y are statistically independent. So we would like to see if they are independent or not. So the procedure will be to find the marginal densities, see if their multiplication equals to the original joint density. So fx of x here is equal to the integration from minus infinity to infinity, 1 over 12 u of x, u of y, e to the minus x over 4 minus y over 3 dx, dy. So you integrate over y, you end up with the function of x. Now, instead of u of y, we will put here 0 to infinity, 1 over 12 u of x, e to the minus x over 4 minus y over 3 dy. So everything in x here is a constant with respect to y because the integration is over y. So this is equals to 1 over 12 u of x, e to the minus x over 4 times the integration from 0 to infinity e to the minus y over 3 dy. And this is equals to 1 over 12 u of x e to the minus x over 4 times the derivative of this one is minus 3 e to the minus y over 3 from 0 to infinity. If you apply infinity here, you have 0, e to the minus infinity is 0. If you apply 0 is 1 with a negative sign, so this is equals to 1/4 u of x e to the minus x over 4. So this is our fx of x. So fx of x is an exponential distribution function. If we do the same thing for y, so we will end up with fy of y is equal to the integration from minus infinity to infinity, 1 over 12 u of x, u of y, e to the minus x over 4 minus y over 3 dx. Okay, u of x is valid from 0 to infinity, so this is integration from 0 to infinity, 1 over 12 u of y e to the minus x over 4 minus y over 3 dx. So we can take 1 over 12 u of y as a constant, e to the minus y over 3 times the integration from 0 to infinity of e to the minus x over 4 dx, and this is equals to 1 over 12 u of y minus e to the minus y over 3 times minus 4 e to the minus x over 4, and this is valid from 0 to infinity. So our fx of x is equal to 1 over 3 u of y, sorry, this is fy of y. Fy of y equals to 1 over 3 u of y e to the minus y over 3. So if we multiply fx of x times fy of y, this is equals to 1/4 u of x e to the minus x over 4 times 1 over 3 u of y e to the minus y over 3, and this is equals to fxy of x and y. So x and y are, this means that x and y are statistically independent. Okay, so they are statistically independent. Okay, sorry. Based on this, we are going to discuss some functions of two random variables. I'm going to discuss the addition of two random variables. So the distribution, this is a subtitle here, talking about the distribution and density of a sum of two random variables. Okay, so we will assume that a random variable w is equal to a random variable x plus a random variable y. So this is what we are looking for. Okay, now I'm gonna discuss the distribution function of this fw of w is equal to the probability that the random variable w is less than or equal small w. This is by definition. This is the definition of the distribution function. Okay, now if I would like to substitute instead of w the probability that x plus y less than or equal small y. So x plus y has a joint density which is f. So this one here, x plus y, has a joint density of x and y. Okay. If we are looking at this one here, we can say that you have a random variable x, you have a random variable y, and w is a variable. So this variable means that this is a range in the xy plane, and it is like this. This is x plus y equals w. So when y equals 0, x equals w. So this value here is w and 0. And the value here is 0 and w. 0 and w. Now, this one here, x plus y less than w, this is the range in the xy plane here. So this is our range in the xy plane. The probability that x plus y less than w, and w is a variable, so this curve here goes down and up according to our w that we will choose. Now, what is going out here in the third dimension is the density function. Here, going out from the whiteboard is fxy of x and y. The density function of x and y so it's distributed in x direction, y direction, so you have actually a surface, and you have a volume under the surface. Okay, so if we would like to find this probability here, so this is fw of w is equal to this probability. So it's a double integral over fxy of x and y dx dy. So if you are doing this dx dy, we know that from calculus we have to take a strip here. This strip here, infinitesimal strip, the strip goes in the x direction from minus infinity, so this is for x equals minus infinity, up to x. This is the x that we are looking for. It's like x function of y and w. So it's x here is w minus y. And this strip that we are taking here, it goes up here and down here from minus infinity in the y direction up to plus infinity in the upper direction. So in the y goes from minus infinity to infinity. Okay? This is known from calculus. When you are integrating over a portion of the xy plane, and this is the third dimension in the z plane, in the third dimension, I mean in the space, three dimension, x and y and z, we have this integration. Now what we are going to introduce here, so to make things a little bit easier, we will, if it is given to us that x and y are statistically independent, so what if x and y are statistically independent? So if they are statistically independent, what will happen? So fxy of x and y equals to fx of x times fy of y. So we can separate those two, this one here, and do two separate integrals. So you have fw of w equals to the integration over y from minus infinity to infinity, fy of y, times the integration from x equals minus infinity to w minus y, fx of x dx and after you evaluate this, you do dy. So this is an inner integration, this is an outer integration. Notice that the upper limit here is y, so you cannot take it outside the integration dy. You have to integrate this inner integral first, find it as a function of y, then do the integration, the outer integration with respect to y. Okay, before we do the integration, I'm gonna go for the derivative of this dfw of w by dw, which is equal to fw of w. So this is equals to d by dw of the whole integration. Integration from y equals minus infinity to infinity, fy of y times the inner integral from x equals minus infinity to x equals w minus y, fx of x dx, and then the whole thing dy. Okay? This, what we will do here is doing the Leibniz rule. Apply Leibniz rule. Let the integration go for the outer integration. The derivative go for the outer integration. The upper limit is constant, the lower limit is constant. So the third term is the only term. It goes to the inner integration. The upper one is a function of w, so it will have a value. The lower one is 0, and the inside here is 0. So the end result that we will get here is an integration from minus infinity to infinity over y, fy of y times fx of w minus y. This is the upper term of the derivative times dy. Okay, so this is what we have. This is fw of w, and if you look at this one here, this is what we call the convolution integral. So this is a convolution integral, and fw of w is fy of y times fx of w minus y. If you are adding two statistically independent random variables, then the density function of their addition is the convolution of their densities. Notice that the convolution integral is commutative, which means that this is also equals to the integration from minus infinity to infinity fx of x times fy of w minus x dx. This can be achieved if you are taking, instead of taking this horizontal infinitesimal strip, you can take this vertical infinitesimal strip and do the integration here dy dx. So y will be from minus infinity to w minus x instead of w minus y, and x is going from minus infinity to infinity. So this is the convolution integral, and this is a very important result that we would like to discuss with you and do some examples. Okay. So we can say that fw of w is equal to fx of x convolved with fy of y. Okay? Given that x plus y equals w. Okay? And yeah, of course, this is also equals fy of y convolved with fx of x. Both, this is a commutative operation. Okay. Let's do an example. I'm going to have f(x) of x as a uniform. This is a 1 over a. So f(x) of x is a uniform, and this is, and f y of y is also another uniform, 1 over b. So you have y, and you have f y of y, and x and y are statistically independent. W is equal to x plus y. Find f w of w. Okay. So we will implement the convolution. So the convolution integral is usually f w of w is equal to the integration from minus infinity to infinity of f x of x times f y of w minus x dx. Which means that we're gonna keep fx of x constant as it is. Fy, we will rename it and fold it and shift it. So fx of x, first of all, I'm gonna keep fx of x as it is. This is from 0 to a, 1 over a. This is the integration, or sorry, the density function of x. Fy of y, this is x, I'm gonna rename it and put it as x. So we will first have it folded. So this is fy of minus x. Yeah, so this is minus b. Now if I'm gonna take it below this one also, so this one will be fw for negative fw minus y. So this one will be like this. This is w, and this is minus b. So if this is w, the width is plus w. So w here is negative. So this one is fx or fw minus x. So fw minus x is like this. Now for w less than 0, you don't have, the amplitude here is 1 over b. Now this is fw of fy of w minus x. Now if we are moving this from w equals to minus infinity up to infinity, we can say that fw of w equals to 0 for w less than 0. Okay? 0 for w less than 0. Now, if w starts to be, so you move it, and now you have w equals 0 here, and this is minus b. So you will start having an overlap. Now you are doing the multiplication of those two. This is the start of having an overlap of those two. So I'm gonna take one like this and put it something like this. So this is my w, and this is my minus b plus w. So you have here minus b plus w. This is the value that we will have here. W, now you have an overlap of this area with this area up to here, up to w. So this area has an amplitude of 1 over b, this one 1 over a. So you do the multiplication and multiply it by the width. You end up with the area of the integration. The integration is the area under the curve of their multiplication. So you multiply those two and then you integrate. So we multiply those two and then we integrate. So our integration will be W over AB. W is the width. The amplitude of this rectangular shape is 1 over A times 1 over B. So this is for W greater than or equal 0, less than A. Yeah? So when this one reaches A, like this, so this is my W, this is minus B plus W. Okay? So this one is okay until we reach this one. Afterwards, so we will have W greater than or equal A. So we'll go like this here. So this is W, this is B minus B plus W. So here, this is true until this W plus B equals 0. So when W plus B equals 0, this means that W equals B, so this is less than B. Now, in this area here, you have a constant 1 over A times 1 over B, and the width here is A. So it's 1 over A times 1 over B times A, so it's 1 over B. So the answer here is 1 over B. Yeah. Okay. Now, if we go beyond this, and now we are having some value like this. So this is W, and this is minus B plus W. But minus B plus W now is going outside. So the range of overlap is from this value here up to A. So this is the overlap, but W will be going from greater than or equal B, less than A plus B. Okay, when A plus B, so you have W equals A plus B minus B, it's A. So you end up here, and it goes outside. If you are here, then what is the area of the multiplication of those two? The area is 1 over A times 1 over B times the width. The width here is A minus B plus W. So this is equals to A plus B minus W over AB. Yeah? So this is A plus B minus W over AB. Yeah? And the last one, when W is greater than or equal A plus B. So this one will be like this. So you are outside here. So this is your W, this is minus B plus W. And you don't have any overlap of this function with this function, so this is equals to 0. So the end result of this, the addition of those two, the density function, is a trapezoid, and this trapezoid has the shape as function of W, 0 below 0, then you have up to A, B, and A plus B. So you have here the amplitude like this, trapezoid like this, and goes down like this. So this is the curve 1 over B, and this is the slope, the positive slope W over AB, and this is the negative slope, A plus B minus W over AB. So the slope here is 1 over AB, the slope here is minus 1 over AB, okay? And so this is how it looks like. One check here, if you need to check your answer, you can find the area under this trapezoidal shape, and the area under this trapezoidal shape is the area of this triangle plus area of this triangle plus area of this rectangular shape. You can add them and you can find out that this is equals to 1. Or you can find it as an area of trapezoid. It's this base plus this length here added together divided by 2 times the amplitude. So we can say that, okay, the whole thing is A plus B plus here is B minus A. So this area, this length here is B minus A. This length here is A plus B divided by 2 times 1 over B. Okay, so the length, this length plus this length divided by 2 times B. So this is 2B over 2 times 1 over B, and this is equals to 1. So we make sure that we have the right answer. Okay, we can conclude here from the statistical independence and the sum of random variables the following result. So if we have a sum of several random variables, so if you have y equals to x1 plus x2 plus x3 plus x sub n, independent random variables, then fy of y equals to the convolution of x1 convolved with fx2 of x2 convolved with fxn of xn. Okay. From this, we can find a very important theorem, which is called the central limit theorem. What does it say? The central limit theorem says the following. The central limit theorem states that the sum of n statistically independent random variables y equals to x1 plus x2 plus x sub n, which has the mean y bar equals x1 bar plus x2 bar plus x sub n bar, and the variance sigma y squared equals sigma x1 squared plus sigma x2 squared plus sigma x sub n squared has probability distribution asymptotically approaches Gaussian as n approaches infinity. Okay, so if you are adding n statistically independent random variables, you are approaching a Gaussian with a mean that is the sum of the means and the variance is equal to the sum of the variances. Very simple example here. We have 3 statistically independent random variables, x1, x2, and x3, which are defined by x1 bar equals -1 and sigma x1 squared equals 2, x2 bar equals 0.6 and sigma x2 squared equals 1.5 and x3 bar equals to 1.8 and sigma x3 squared equals 0.8. Okay? Okay, so we need to write the equation describing the Gaussian approximation for the density function of the sum x equals x1 plus x2 plus x3. Okay, so because they are statistically independent, the density of the summation is approximated by Gaussian. So as a solution, we can use the central limit theorem using the central limit theorem. We can say that x bar equals to x1 bar plus x2 bar plus x3 bar, and this is equals to -1 plus 0.6 plus 1.8, and this is equals to 1.4, and sigma x squared equals sigma x1 squared plus sigma x2 squared plus sigma x3 squared. This is equals to 2 plus 1.5 plus 0.8, and this is equals to 4.3. This means that our random variable x, which is the summation of those three, belongs to a normal of a mean of 1.4 and a variance of 4.3. Of course, this is an approximation because you are adding only three random variables. The Gaussian is asymptotic for n equals infinity. If you want to do the exact, you have to do the convolution of those two together, and then you convolve with the third random variable. So you do the convolution twice, x1 with x2, then you take their resultant of the convolution and you convolve it with the density function of x3. But this is a good approximation, and it's really valid. So this is the random variable is a normal or Gaussian, and our fx of x is equal to 1 over square root of 8.6 pi, which is 2 pi times 4.3 sigma x تربيع, sigma x squared, e to the minus x minus 1.4 squared divided by 8.6, and this is valid for x between minus infinity and infinity. So this is the density function of the summation of those three random variables, giving those means and those variances, and the new random variable is the addition of those three random variables. Okay? With this, we conclude our discussion about the independence of random variable, and meanwhile, we also discussed the central limit theorem, which is related very much to statistically independent random variable, the addition of statistically independent random variable. I would like to thank you very much for being with me. I would also thank you, and I hope that you will find this lecture interesting. We'll see you in next one.